We spend so much time looking out there, at the stars, the galaxies, all the bright stuff.
Uh-huh. Visible universe.
Exactly. But holding it all together, actually shaping it, is this other thing, dark matter. We can't see it at all.
Right, and it's, what, something like 85% of all the mass in the universe? It's huge.
It's staggering, yeah. And it's just
Unbelievable.
invisible, a total mystery, really. Okay, so let's get into this. Today we're doing a deep dive into, well, a pretty radical new idea about where this stuff might have actually come from. Forget the usual picture, dark matter just being these sort of cold, heavy particles floating around.
Right, the sort of default assumption for a long time.
Yeah. This new theory, it suggests a crazy twist, that maybe dark matter started out almost like light, way back in the early universe.
And then transformed.
And then somehow transformed into the lumpy dark matter we think shapes galaxies today. It's quite a shift.
It really is. I mean, it flips the standard picture on its head. The usual thinking is dark matter was always, well, dark and cold and slow. But this new work is from Robert Caldwell, a professor at Dartmouth, and a student, Guanming Liang. It just came out in Physical Review Letters.
Okay.
And their core idea is maybe dark matter actually grew out of these incredibly energetic, almost massless particles right after the Big Bang.
Like light, you said.
Almost like light, yeah.
Yeah.
Very similar properties initially. And the theory is these things somehow bumped into each other, cooled off really fast, and, gained mass.
Wow.
Became those cold lumps.
Wow, Caldwell actually summed it up perfectly, didn't he? He said something like,
Yeah, he said, dark matter started its life as near massless relativistic particles, almost like light.
Right. That's totally antithetical to what dark matter is thought to be.
Oh, yeah.
It is cold lumps that give galaxies their mass.
Our theory tries to explain how it went from being light to being lumps. It's a fantastic quote.
It really is. Just think about that. Something acting like light becomes the, invisible skeleton of the cosmos.
Yeah,
That's a big conceptual leap.
It is.
So, okay, to get our heads around this transformation, what was the universe actually like back then?
But right at the beginning.
Right. We need to go way back. We're talking moments after the Big Bang. Okay, so about 13.7 billion years ago.
Unimaginably long ago.
Totally. And the conditions. Just picture pure chaos. Unbelievably hot, unbelievably dense. It wasn't stars and galaxies. It was just this roiling soup of fundamental particles.
Ectoplasm.
Even hotter and denser than that initially. And it was dominated by particles moving incredibly fast, very close to the speed of light, things that acted a lot like photons, the particles of light. Massless, energetic.
Okay, so this primordial soup of almost light particles buzzing around like crazy.
Exactly.
So how did these things, which you said were almost massless, suddenly become the heavy, influential dark matter that, pulls galaxies together? What's the actual mechanism they're proposing? Yeah, that's the absolute core of it, isn't it? And this is where the theory gets really interesting. Caldwell and Liang suggest that these particles, even though they were zipping around, started to, pair up. Bond together.
Bond how?
They think it has to do with a property called spin. You know how magnets have north and south poles?
Opposites attract.
Kind of like that, yeah. They propose particles with opposite spin directions would be drawn to each other in that incredibly dense environment.
Right.
That's step one, this pairing.
Okay, so they start linking up, but they're still almost massless at this point.
It's basically massless, yeah. The real change, the thing that made them become dark matter as we think of it, happened as the universe expanded and started to cool down.
Okay. The cooling. That makes sense. Everything was insanely hot, but expansion means cooling off.
It had to cool. So imagine these paired up, nearly massless particles. As the universe cools, they start losing that intense energy they had. And this is the kicker. They describe it as an energy plummet, a really sudden, dramatic drop in energy for these pairs.
An energy plummet.
And here's where Einstein comes in, right?
Huh.
Yeah, immencio here. Energy and mass, they're interchangeable.
So as they lost
They
energy.
gained mass, the energy had to go somewhere, and essentially converted into mass. Liang used a great analogy,
What was it?
like steam cooling rapidly and condensing into liquid water. It's a phase transition, a fundamental change of state.
Steam into water. Wow. Okay.
Yeah, he said, the most unexpected part of our mathematical model was the energy plummet that bridges the high-density energy and the lumpy low energy.
So it's like a cosmic switch got flipped. High energy, almost no mass. Then whoosh, cooling happens, energy drops, and suddenly there's mass.
That's the picture they're painting. And this phase transition, this sudden mass gain. That's how they explain the sheer amount of dark matter we see today.
Right, because we need a lot of it to explain the universe's structure.
Exactly. Caldwell pointed out, this phase transition helps explain the abundance of dark matter we can detect today. He said, it sprang from the high-density cluster of extremely energetic particles that was the early universe.
So you start with a universe full of these light-like things, they pair up, cool down, bam, phase transition, and suddenly you've got enough dark matter mass to build galaxies later on.
That's the proposed history, yeah.
Okay, but this idea, massless things suddenly gaining mass through pairing and cooling. Is there anything, like anything we actually see in physics that works kind of like that? Does it have any parallel?
That's a really important question for any new theory.
Mm-hmm.
And they do point to something, superconductivity.
Superconductivity, like electricity flowing with zero resistance.
Exactly that. You know how that happens at really, really low temperatures in some materials?
Yeah.
Well, it involves electrons, which normally repel each other, actually forming pairs. They're called Cooper pairs.
Cooper pairs.
And
Sorry.
these pairs sort of condense, and there's a distinct drop in energy associated with their formation. It allows them to move without resistance.
Ah, so it's an example of particles pairing up and having an energy drop at low temperatures.
Precisely. Caldwell explicitly said they looked at superconductivity for clues. He said, we looked toward superconductivity for clues as to whether a certain interaction could cause energy to drop so suddenly. He added, Cooper pairs prove that the mechanism exists.
So it's not the same. Obviously, electrons aren't dark matter.
No, definitely not.
Yeah.
But it's an analogy. It shows that nature does have mechanisms where particles can pair up and undergo these sudden energy shifts when things get cold enough. It lends plausibility to the core idea.
Okay, that makes sense. It provides a sort of physical precedent.
Exactly.
Right, so we have these super fast relativistic particles pairing up. Then this dramatic cooling, the energy plummet, gaining mass. Lang had another analogy for this whole process, didn't he? Something about breakfast.
Huh? Yeah, he did. It's quite memorable. He compared the early universe, full of those high-energy light-like particles, to a shot of high-energy espresso.
Okay, I like that. Full of buzz.
Right. And then the dark matter we have today, these sort of cold, clumpy structures holding galaxies together, that's the cold cosmic oatmeal.
High-energy espresso to cold cosmic oatmeal. That's brilliant.
It really paints a picture, doesn't it, of this huge drop in, like, overall energy density as the universe expanded and cooled, but at the same time, an increase in the density of mass locked up in these structures.
It makes a really abstract idea feel much more graspable. Okay, but analogies and plausibility are one thing. The real test for any scientific theory is, well, can you test it?
Crucial point, yeah.
So how could we ever find out if this is right, if dark matter really did start out like light? Is there any way to check?
And this is maybe the most exciting part of their proposal. They say, yes, it is testable.
How?
They argue that this specific process, this transformation, would leave a faint but unique signature on the cosmic microwave background, the CMB.
Ah, the afterglow of the Big Bang, the oldest light in the universe.
Exactly. It's like a snapshot of the universe when it was just becoming transparent, about 380,000 years after the Big Bang. Tiny variations in that light tell us incredible amounts about the early conditions.
So they think their specific kind of dark matter particle, formed in this way, would have subtly affected that ancient light pattern.
That's the prediction. They believe these extremely low-energy dark matter particles, resulting from that phase transition, would imprint a very specific, faint signal onto the CMB fluctuations.
Wow. So if we could find that specific signal...
It would be huge. It wouldn't just support their theory, it could fundamentally change how we think about the universe's first moments and what dark matter actually is. It could open up completely new physics.
Okay, so we're looking for a tiny fingerprint on this ancient light. Is that feasible?
Yeah.
Do we have telescopes or projects that could actually spot something that subtle?
Well, according to Caldwell, yes. Data we already have from past CMB missions might hold clues, but more importantly, upcoming projects are designed for exactly this kind of precision.
Like what?
He mentioned things like the Simons Observatory being built in Chile, and another big one called CMB Stage 4. These are next-generation experiments aiming to map the CMB with unprecedented detail.
So they might actually be able to see this signature, if it's there.
That's the hope. They're specifically looking for tiny anomalies and subtle patterns. Caldwell put it simply, it's exciting. He said, we're presenting a new approach to thinking about and possibly identifying dark matter.
It really is exciting, like searching for the echo of dark matter's birth cry in the oldest light. Incredible.
Yeah.
Now, you mentioned this came from Caldwell and Liang. How did they even come up with this? What was the spark for such a, well, such a different idea.
It's actually a neat story of connecting dots. Apparently, Liang read a paper from early 2023 about looking for signs of Cooper pairs, like in superconductors in the early universe.
Ah, linking back to that analogy.
Right. And he got curious if the authors had thought about what happens if the temperature isn't absolute zero, more realistic conditions. They hadn't, apparently.
Okay.
But then Liang was also taking a class on solid-state physics, the physics of materials.
Seems unrelated to cosmology at first glance.
You'd think. But in that class, he learned about a particular mathematical way, a framework, that could actually extend that Cooper pair model to work at non-zero temperatures.
Whoa, serendipity.
Kind of. So he teamed up with Professor Caldwell, his advisor, and they basically plugged this solid-state physics math into the early universe Cooper pair idea.
Yeah.
And Liang said, Professor Caldwell and I plugged in the math to see what it said. And his description was great. It told the whole story. It fleshed out this rich evolutionary history of particles from the high temperatures of the early universe to the lower temperatures today.
Wow. The math just laid it all out.
Seems like it. He also gave a shout-out to the professor of that solid-state course, Rufus Boyack, for providing that key mathematical tool. It's a cool example of how ideas from totally different areas of physics can cross-pollinate.
Yeah, cosmology meets condensed matter physics. That's not something you hear every day. And it sounds like the maths itself wasn't overly complicated.
That's what Liang emphasized, yeah. He mentioned the model's beauty lies in its relative simplicity. He said, the mathematical model of our theory is really beautiful because it's rather simplistic. You don't need to build a lot of things into the system for it to work.
So it doesn't require inventing lots of new particles or forces?
Apparently not. He finished by saying, it builds on concepts and timelines we know exist, which, often makes a theory more appealing in science if it works elegantly without needing too many extra assumptions.
Right. Simplicity and elegance. Okay, so let's just pull this all together. We started with dark matter, this huge, unseen chunk of the universe.
The invisible scaffolding.
Yeah, and this new theory challenges the idea that it was always just cold stuff. It suggests dark matter maybe started out like light, super energetic, almost no mass.
Right after the Big Bang.
Then as the universe cooled, these particles paired up, maybe because of spin, and went through this dramatic energy plummet.
The phase transition, like steam to water or drawing on the Cooper pair analogy from superconductors.
And in that plummet, they lost energy but gained mass, becoming the dark matter we, don't see today, but know is there.
And explaining potentially why there's so much of it.
And the really cool part, it might be testable by looking for a specific faint signature in the cosmic microwave background.
With new telescopes coming online, we might actually get an answer relatively soon. Maybe.
It's a fantastic possibility.
It really is. Just the notion that something so fundamental, the stuff that dictates where galaxies form, could have had such a different beginning. It's pretty mind-bending.
It makes you rethink things, doesn't it?
It forces you to question assumptions about how fixed things are, how dynamic the universe's history really might have been.
Definitely. And it leaves you thinking, if dark matter, this seemingly constant, invisible presence, could have started as something almost like pure energy.
Right.
What else? What other fundamental parts of our reality might have histories that are way stranger and more dynamic than we imagine? It's something to ponder next time you look up at the sky, isn't it? Wondering about the hidden history written in the darkness between the stars.